This video is going to be about a method we call the washer method. So in the washer method, that's like a washer, I don't know if you've, like nuts and bolts, there's a washer, so it's a ring within a ring. So this is that kind of idea. This is one I accidentally was showing you before because I forgot to change the axis of rotation. So we're going to still use the function 4 minus x squared over 4 and g of x equals 2. So it's still that region up above, but we're rotating around the x-axis. So I took the liberty of flipping that region or reflecting that region over the x-axis because that's what we're rotating about. And then if I try to make this three-dimensional, it's really hard for me to draw these three-dimensionally. Imagine a solid bead, if you will, with a hole in the middle. And I was starting to show you this in my app before, so let me show you in my app now. I put in everything we needed. So it's the function f of x is 4 minus x squared over 4, g of x is 2. The axis of rotation is going to be 0 because that's the x-axis. The number of intervals means how many cylinders do I want to put in this. And I kind of hastily showed you that last time. And so we get kind of, it's almost that football shape, except things are cut off a little bit because we've got a hole in the middle. So here's my shape. It's kind of cool. This is what they call the washer method because we're going to find the volume of a cylinder that has a hole in it. Okay, so this is the shape we're going to calculate, this volume, how much of that is taken up. And when I hit the plus sign, it just adds more and more rings to it. You can see that those cylinders are getting skinnier and skinnier because I'm adding more of them. So dx is approaching 0. This becomes more of a solid shape than chunky cylinders. And if you notice at the bottom of my screen, the volume is getting more and more accurate. So it looks like we're approaching 132.7-ish. Okay, so let's do this by hand, of course, because you're not going to have this app on you. We're going to do this a different way, the same but different. Think about like when you were in geometry, when you had, this is just an aside, remember when geometry you had like a square with a circle inside, and how do you find the area of all of this? And you would find the area of the square, you'd find the area of the circle, and you would subtract them. Well, this is going to be the exact same methodology, and that we're going to find the volume of this shape as though it were solid, and then we'll take away the volume of the part that is being removed. So if we were to think about this shape as though it were solid, the solid shape is from the very top of the figure all the way to the very bottom of the figure. Notice, even though I've been teaching this for umpteen million years, I draw this picture every single time. And I highly recommend you do the same thing. Okay, so if this thing were solid, my cylinder would reach from the very top of the shape, so I make sure my cylinder touches the top and my cylinder touches the bottom, because that would be the solid shape. Now, for the part that's in the middle, yes, I understand it's a cylinder, but it won't always be a cylinder. So inside of this, I need to find the volume of this part that's being taken away. So I made sure I drew my representative cylinder from the top of that part that's taken out to the bottom of the part that's taken out. That's going to really make sure I have the correct radius. Okay, so the height for each of these is dx because these are all horizontal. They're horizontal distances, so it's dx. Everything's in terms of x. The radius of this larger cylinder, I'm going to use a big capital R. The radius of this one is f of x. It's the bigger function, the top function, 4 minus x squared over 4. The radius of this one is the bottom function. In this case, that's 2. We already know where they intersect. They intersect at negative square root of 8 and positive square root of 8. So we'll still integrate from there to there. So here's what we're going to do. We're going to take the volume of the entire solid. So this is the volume of the whole thing. And that's pi times the big radius, 4 minus x squared over 4 squared times the height. And we're going to subtract away the volume of the inside. And the volume of the inside is negative square root of 8 to positive square root of 8 pi times the radius squared times the height. So that's one way you can write this. You can also write this, you can combine them because they have the same bounds. They're both from the negative square root of 8 to the positive square root of 8. They also both have a pi in common. So if I take the pi out, I could also write it like this. And then dx for both of them. So there's two ways to do it. Just knowing that, that there are multiple ways to look at it is totally fine. And now you just find the antiderivative, just like we've been doing. You would square this and then subtract that and then use the power rule from there. Plug in square root of 8, plug in the negative square root of 8. That's the washer method. Okay, I want to show you one more. This time the volume is going to be, or the region is bound by y equals 6 minus 2x minus x squared and y equals x plus 6. And we're rotating at about the line y equals 3. I want you to go take a minute. And I want you to try to draw this and see if you can draw your representative cylinders to see what this is going to look like. Okay, welcome back. I hope you actually did that. The first thing I want to do is look at where these two functions intersect each other. So I'm going to set these two equal to each other. It's going to help me with my picture. I like my x squared to be positive. It's easier for me to factor, so I'm going to add the x squared over. I'm going to add 2x over, so that's 3x, and if I subtract 6, that's 0. So now if I factor this, I have two places where these lines intersect, and that's or where these curves intersect. One is at 0, the other is at negative 3. So if I draw this, oh, that's a horrible line. At 0, I know they're going to intersect at 6 because that's the y-intercept of the linear function. 2, 3, 4, 5, 6. And I know that they also intersect at negative 3. Negative 3 plus 6 is positive 3. So they're going to intersect here. I've got this straight line, and then I've got that. Okay, so now we've drawn the shape. This is the region that's being rotated. And we're going to rotate that about the line y equals 3. Okay, so I'm going to draw in the axis of revolution. The line y equals 3 is here. Here comes the fun part. Now we're going to reflect this about that line y equals 3, just to get a better idea of what this shape is going to look like. And then this is circular because we rotated it. So it's kind of this, it's this outer shape here is solid. And then this part inside, let me get a different color to show you. This part inside is empty. That's empty. That part's going to be taken away. So it's kind of a bowl if you look at it that way. It's a bowl that with the part taken out. Anyway, so let's see if we can find the volume of this. I'm going to draw in my representative cylinders. So we've got the cylinder as though this whole thing were solid. So I'm going to draw a cylinder from the very outer function, the very top to the very bottom. And then we're going to take away this part that's on the inside. Yes, I know it's a cone, but we're going to use calculus because it won't always be a cone. So I'm going to find these two radii, and we're going to then find the volume of this entire thing. So we know that the height of each one is dx. That means everything needs to be in terms of x because the height is a horizontal line. I can find the radius of this bigger one, of the solid, because I know that it's the function 6 minus 2x minus x squared, but it's not all of that, because 6 minus 2x minus x squared would go from the top of this curve all the way to the x-axis. but there's part of that missing because we start the radius at the line y equals 3. So I didn't leave myself enough room. This big radius then is 6 minus 2x minus x squared minus 3, because we're only starting at the line y equals 3 and going up from there. Similarly, for the inner part that's being taken out, so I'm going to call this my little r, it's the function or the line x plus 6, but not all of it, because we don't start that line from the x-axis. We start it from the line y equals 3. Okay, if we now find the volume we found where they intersect, that's from negative 3 to 0, pi. The big radius is 3 minus 2x minus x squared, once I simplify, squared times the height, minus negative 3 to 0, pi times the little radius, x plus 6 minus 3 is x plus 3 squared times the height. And remember, you could always write this as one integral, and it's not bad practice to see it that way and try it that way. So it's 3 minus 2x minus x squared minus x plus 3 squared. My recommendation is to simplify both of those, square them, and then combine them, and then find the antiderivative. Okay, that's the disk and the washer. So this was the washer method. The washer means there's a hole in the middle, and I've solved 2 different washer method problems. It's basically just finding the volume of the whole solid, subtracting away the volume of the part that